Hello mathematicians, puzzlers, and other curious people. In this video, we are talking about commutativity, which is the ability to, like your morning commute, move back and forth some parts in a math problem without changing the value. So commutativity is a property of some operations but not others, and let's start with a list of operations and find out which ones are commutative. So I've got 5 operations listed here: addition, subtraction, multiplication, division, and exponentiation. A lot of people stop listing operations at division. I say, well, raising to a power is an operation. It's a thing you do with 2 numbers. It's a binary operation. Let's consider it and find out if it's commutative. I'm going to start by using some examples. I will be able to tell from examples whether something is definitely not commutative. For the ones that don't get kicked out by an example, I will turn around and use some logic based on what we know about that operation for all numbers, because I don't want to have to test out every pair of numbers. I want to use some reasoning. But before I knock myself out on the reasoning, I want to get rid of the ones that don't make sense. I'm going to try 4 plus 3, and that's 7, and 3 plus 4, and that's 7. So addition could be commutative. So now let's try subtraction. I'm going to try 7 minus 5, and that's 2. I will also try 5 minus 7, and that's negative 2. So it's kind of a related number, but it's not the same number. So I know subtraction is not commutative. It's order sensitive. Changing the order changes the result. Now let's try multiplication. And I am going to try 3 times 4, which is 12, and 4 times 3, which is also 12. So multiplication could be commutative. Let's try division. 12 divided by 6 is 2. We got another 2. But then on the other hand, 6 divided by 12. And don't let this scare you. It's showing the division as a fraction because a fraction is a division problem in disguise. So 6 divided by 12, well, that's 0.5. So division is definitely not commutative. Last but not least, exponentiation. So let's try 2 to the power 5, and then let's try 5 to the power 2. 32 and 25, not the same. So I know from an example that exponentiation is not commutative. Now let's move on to thinking about whether this is truly a commutative operation in the case of addition. So when I think about addition, I think about a pile of rocks. Let's say we have a pile of 5 rocks. If I pick up 2 rocks first and then 3 rocks second out of that pile, I still have 5 rocks. But on the other hand, if I pick up 3 rocks first and then 2 rocks, I have 5 rocks. So since you're taking pieces of the same overall pile, it's always the same total. So I would say yes, addition is always going to be commutative, because as soon as you push 2 groups of rocks together to make a pile, well, it doesn't matter if you push them together in one order or the other order. So the formula for addition would be A plus B equals B plus A. And again, we're saying that means you can add things in either order and it'll come out the same. And our example of that was that 4 plus 3 equals 3 plus 4. But that's just an example. If you put 2 plus 6, that should be the same as 6 plus 2. If you put 89 plus 75, you know without even figuring out that total that it would be the same if you had 75 plus 89. Now for multiplication, the rock example could work for whole numbers if you wanted to line them up in rows, but I like a little bit more flexible example. So when I think about multiplication, I think about a table. Not like a times table, but like a table that you can spread your work out on and work at. So how much space do you have on that table? Well, the area of a rectangular table is its length times its width. What if you rotate the table so that its length and width trade places? You still have the same amount of area on the top of the table, even if you rotate the table. So no matter which one you call the length and which one you call the width, no matter which side of the table you measure first in multiplying to find out its area, the area comes out the same. So we expect to see that, in fact, A times B is the same as B times A, and we expect to see that for any two numbers that we multiply, such as our examples 3 times 4 and 4 times 3. Commutativity is really useful. You can use it to make problems easier to solve by rearranging them into an order so that pieces that fit together nicely are next to each other, so then you can do those calculations first. So keep commutativity in mind anytime you have a long series or even a shorter series of additions or multiplications you need to do. And other than that, calculator.